So a transformation of functions happens when you put a multiplication factor either in front of the function or inside of the operator in order to modify the effectiveness of the x value within the function, or to modify the effectiveness of the function's output when you graph it. So what that looks like is expansions and compressions either horizontally or vertically of the basic pattern. So where translations were simply moving the thing around, a transformation actually dilates or compresses the function and changes its shape. That's what this sort of the Latin means. Trans is to move across, and formations is shapes. So you're moving across the shapes. So it will actually be a change in shape. All right, so the first translation or transformation we're going to do is a vertical stretch, and I'm going to use a logarithm to show you that one. So I need my basic pattern for log. So you're going to have to think about those x values that work really well for log. So the first one is at 0, there is a vertical asymptote. And then the x values that are really nice will be 0.1, 1, and then 10. So the log of 0.1 is -1, and the log of 1 is 0, and the log of 10 is 1. You can check those with your calculator. So what I've got in these charts here then are some x values, and then I have the log of those x values. And the function that we're going to try and sketch is g of x is 3 log x. Now you notice it isn't log x plus 3, it's 3 times log x. So when you see a number multiplying in front, it is affecting the function vertically, because you are taking the output of the function and then increasing it. So when you see a number out here that is a whole number, or a number greater than 1, let me note that down. This is your a value, right? The a value out there in front is what determines the vertical stretch or compression. This particular one has an a value that is greater than 1. So if you see a number out here like 2 or 5 or 7/3, anything that is bigger than 1, you end up with a vertical stretch. Which means it's going to get taller than it normally would be if it's above the axis. The thing you also have to remember, though, is that anything below the axis goes deeper. So it's taller / deeper. All right. So if I were to fetch myself a grid and get my axis on there, the basic log function, which I have over here, has a vertical asymptote at 0. When x is 0.1, log is at -1. When x is 1, log is 0. And when x is 10, log of 10 is 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1. Now, I could sketch that in. I'm going to do the transformation first so that I don't get lines all over the place on my grid. So mathematically, the way you do this these numbers are log x. What I'm trying to sketch is 3 log x. So all I have to do is take these numbers and triple them. So -1 times 3 would be -3. 0 times 3 would be 0, and 1 times 3 is 3. And a vertical asymptote which goes to -infinity will be -infinity times 3, which is just -infinity. So what I've got here then is this dot, this one right here, that used to be at 0.1 -1 will be at 0.1 -3. And you see that's this thing. This dot was under the axis, so it is forced deeper. It is forced further away from the axis than it already was. This dot was right on the axis, so it doesn't matter. You stay right there. If you're 0 away and you make that 3 times farther, you're still 0 away. This dot was up 1, so if I triple that, make it 3 times further away, then it's up here. It is 3 times taller than it used to be. So now that I've got these dots still lining up in the logarithm pattern, I just need to color them in. So if you can see the original log passing through here, maybe I'll just dot it in for you. Do you notice that on this side of the intercept, that the pink line, the transformed logarithm, is deeper than the original was? And on this side of the intercept, the transformed function is taller than the original was, as predicted up here. For the next example, I'm going to use the base function 3 to the exponent x. So I'm going to have to make my table of basic values. So for an exponential, we usually use -1. That's a 2. -2, -1, 0, 1, and 2. And I'm not going to bother with 3 because 3 cubed would be 27, which is way off my grid. Well, what the heck? Let's put it in. So 3 to the -2 would be 1 over 3 squared. That's 1/9. 3 to the -1 would be 1 over 3. 3 to the 0 is 1, because anything to the exponent 0 is 1. 3 to the power 1 is 3. 3 squared is 9, and 3 cubed, as previously advertised, is 27. So that's 3 to the exponent x. So the function I'm going to try and transform then would be g of x is 1/2 of 3 to the exponent x. So I look at this number here and I notice that it is outside of the function and it's a multiplication factor. That makes it an a value. And this number here happens to be less than 1. So I have an a that is still a positive number but is less than 1. That means that it will be a vertical compression. Which means that when I'm done sketching this thing, the function should be shorter. Anything above the axis will be closer to the axis than it used to be, or shallower. Anything that was under the axis will be drawn up closer to it. So if I were to fetch my axis, get my untranslated axis on there. At -2, I used to be at I used to be at 1/9. At -1, I used to be at 1/3. At 0, I used to be at 1. At 1, I used to be at 3, 2, and 9, 3, 4, 5, 6, 7, 8, 9, and 3 and 27, which is way off my grid. So these dots, after I apply this transformation, should be getting shorter or shallower. So I should expect this function to be squashed closer to the axis. So how much am I squashing it by? Well, these are the values of 3 to the exponent x, and I only want half that. So half of 1/9 is 1/18. Half of a third is a sixth. Half of 1 is a half. Half of 3 is 1.5. Half of 9 is 4.5. And half of 27 is 13.5. So when x is -2, instead of a 9th, I'm at an 18th. I can't really tell the difference over here. Instead of a third, I'm at a 6th. Again, it's hard to tell. Instead of 1, I'm at half. Instead of 3, I'm at 1.5. This is where I start to see the difference in the behavior. At 2, I'm at 4.5. So 1, 2, 3, 4.5. It's about there. And when x is 3, I'm at 13.5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.5. So if I sketch that in, I still have this horizontal asymptote here. And my exponential takes off like so. This thing used to have a horizontal asymptote and then take off like this. And then by the time I got to this grid point, I was way off. So you notice that the transformed function is shorter or closer to the axis than the untransformed version was. For the third example, I'm going to use a rational function. So I'm going to need to generate my basic pattern for this one. With the rational, we were using -2, -1, 0, 1, and 2. Because all of these numbers end up as fractions anyway, so it doesn't matter which ones you pick. We're going to remember that 1 divided by 0 is infinite or undefined, so there's a vertical asymptote here. And so the function I'm going to sketch then with my transformation is g of x equals -5 over x. Now that doesn't look like a normal a value, so I'm going to factor it out in front. So it would look like this. So if I do that, because -5 times 1 over x would be -5 over x. If I write it this way, I can see that it's a number in front multiplying. It is not inside the function. That makes it an a value. And it is an a value that is less than 0. Now when you have an a value less than 0, I'm getting a reflection. And since it's an a value, it's a reflection this way, right? It affects the vertical direction. So what used to be up is now down, and what used to be down is now up. So I'm going to write the reflection. So vertical reflection. And since this number is greater than 1, just like the positive a values, if it's greater than 1, it's a magnification. So not only will this thing be flipped, but it will be flipped and then all of the dots will be pushed further away from the axis than they normally would be. So I'm going to need a graph here. And plot on my axis. So this one used to be at -1/2, this used to be at -1, this used to be at 1, and this used to be at 1/2. That's 1 over the x value. What I'm trying to sketch is these numbers, 1 over x, but multiplied by -5. So if I do that, -5 times that thing, -5 times -1/2, well, negative times a negative is positive, and 1/2 of 5 is 2.5. 5 times 1 would be 5. This remains an asymptote. 1 times -5 is -5. And -5 times 1/2 would be -2.5. So my dots used to be at -1/2, -1, and then a vertical asymptote this way. And it used to be 1/2 on this side, 1 on this side, and a vertical asymptote on that side. That was the basic pattern, and then you would do this. Now that I've applied this transformation with the vertical reflection, at -2, I should be at 2.5. So this dot got reflected, so it would be up here, and then it was made 5 times further away, landing at 1, 2.5 squares above the axis. This dot, 1 below, was reflected to 1 above, and then made 5 times further away from the axis. So instead of 1, it's 1, 2, 3, 4, 5. This asymptote down here used to head downwards, but then is reflected. So it is heading upwards. This dot used to be 1 above, reflect it, it's 1 below, and then quintuple its distance. Instead of 1, we're 5. 1, 2, 4, 5. This one, reflected, and then quintupled, ends at 2.5. And this vertical asymptote ends up down here instead, giving us a function that looks like this. So just penciling in the original. Notice that the entire thing has been flipped this way. So there's a reflection. What was up is now down, what was down is now up. And these distances have been made taller because of that factor of 5.
To sketch a transformed sine function, we're going to have to work with the sine pattern a little bit. So a sine pattern fits inside of a box that is 360 degrees long. It's a full cycle. It's like a trip all the way around a circle. That box has a midline, and your sine function fits in it like this. It zeroes out on both ends and zeroes out dead center. It has a peak halfway between those and a trough halfway between those. So you end up with 1, 2, 3, 4, 4 equally sized sections. So once you draw this box, you just have to cut it up into 4 bits. So I need to get that box onto this grid here first. So I'm going to draw myself an axis, like so. Y-axis. Now this shape is 360 units long. If I use a scale that goes 1, 2, 3, 4, 5, I'm never going to get there. So I have to jump by a sizable chunk on each one of these grid lines in order to actually fit 360 on there. So generally, the one I found that works best is if every step that way, you call it 30 degrees. So this isn't 1, it's 30. 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. And going the other way, 30, 60, 90, 120, 150, 180, 210, 240, 270, etc. Now, if I've already changed the X scale, I'm going to change the Y scale as well, just so I can get a curve that's tall enough that I can really see what's going on. I'm going to use 0.5 as each step on my Y-axis. So 1.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.55, negative 1, negative 2, negative 3, 4, 5. Okay. So the first thing I'm going to think about drawing is sine of x, not sine of 2x. So to do that, I need to get this rectangle on here. But there's been no translation, so I'm counting from the basic axis. I need to draw a rectangle that's 360 degrees long. So I go out to 360 degrees here. And I'm going to draw myself the back end of this rectangle. Then you can see that the curve is going to have a line where the peaks land, and it is up 1 from the midline, and the troughs land down 1 from the midline. So I'm going to draw that in. So I know that all my peaks will land on this line. All of my troughs will land on that line. Now, if we were just sketching sine x, I would just have to map this pattern into this rectangle. 0 out at the beginning, 0 out at the end, 0 dead center, peak halfway, trough halfway, and then I would have my curve. But sine 2x means that there are 2 full cycles in 360 degrees. This number here, the k value, that makes the function faster. Right? The x's are happening twice as quickly as they normally would. So you get twice as much function in the same amount of space. So to handle that, I'm just going to take this rectangle here, and I'm going to allow for there to be 2 full cycles. I'm going to split it into 2 even pieces. So 1, 2, 3, 4, 5, 6 squares each. So if I go this way, 1, 2, 3, 4, 5, 6, here. 1, 2, 3, 4, 5, 6, here. Right at the edge. And now that I've established this little rectangle here, I have to fit this pattern into this shortened box. So the pattern was 0 out at the beginning, 0 out at the end, be at 0 exactly halfway. Your first peak happens dead center between these 2 dots, and your trough ends up exactly halfway between these. So you've got enough there that you can draw in your sine curve. And you can see my choice of using half a unit per notch on here has made it tall enough that I can actually see that it curves. Once you have it in one box, you have to put it in all the rest of them. So 0 at the beginning, 0 at the end, 0 in the middle, 2, 3, 4, 2, 3. Peak halfway, trough halfway. Next box, start 0, end 0, 0 halfway, peak in the middle, drop in the middle, connect the dots, and start at 0, end at 0, halfway, 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 and you get a beautiful picture of a sine curve. And most of that work was setting up the grid, trying to figure out that you should step by 30s and go up by halves. Counting out a rectangle. And once you get the rectangle counted out, you just have to plot those 5 dots in there and then make your way through.
So the next one will be a parabola. So I need to generate my basic pattern for that. Basic pattern for parabolas. Just use -3, -2, -1, 0, 1, 2, and 3. And then -3 squared is 9, -2 squared is 4, 1, 0, 1, 4, 9. So the function that I'm going to sketch with the transformation is g as a function of x equals 1/3 of x squared. Now, do you notice that there is a multiplication factor in this one inside of the square? So if you have a multiplication factor inside the function, it is a k value. And in this particular case, I have a k value that is greater than 0 but less than 1. So the way to interpret that is that your x values, before I get to square them, I have to cut them in 3. So I've already limited their effectiveness, which means I have to go further out the axis in order to get the same punch from my function. So this one here, this -3, if I pop a -3 in here, the first thing I have to do is divide it by 3, and I get -1. So this value, right, my 1 up on the axis, isn't going to happen until this x value. So I'm taking those values, those dots, and I'm pushing them out from the axis. So if I have a k value that looks like that, this will be a horizontal stretch. And for a k value of 1/3, it means that they will be 3 times farther from the axis. So I'm going to grab my grid then. Put on my untranslated axis. Now my basic pattern for a parabola is 0, 1 and 1, 2 and 4, 3 and 9, 4, 5, 6, 7, 8, 9. This horizontal stretch is saying that I have to take these dots, and however far they are from the y-axis, I have to make them thrice that, because it's a third. So this dot is right on the y-axis. It doesn't go anywhere. These ones are both 1 square away. If you're 1 square away and I triple it, then you should be 3 squares away. So 1, 2, 3. 1, 2, 3. These two dots are 2 squares away from the y-axis, so triple that would give me 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. These dots are 3 away. Triple 3, you get 9. So 3, 4, 5, 4, 5, 6, 7, 8, 9. 3, 4, 5, 6, 7, 8, 9. So I end up with this parabola that's been dilated outwards, right? Pushed away from the y-axis. So if I sketch those in there, it looks like this. So applying a transformation to a square root function, we're going to need to have my basic pattern. And for square root functions, we didn't bother using any x values except the ones that had nice square roots, which means no negatives are allowed. I start at 0. 1 is a perfect square, so is 4, 9, 16, 25, etc. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2, 3, 4, 5. So the function that I'm going to sketch then is the square root of 3x negative 3x. Now, you notice that that is a multiplication factor, and that multiplication factor is inside of the function. That makes it a k value. And a negative in either an a value or a k value ends up being a reflection. And so since it's a k type transformation, this will be a horizontal reflection. And because this k value is a number bigger than 1, I'm going to end up with my x values being more effective than they normally would be. That's going to pull the function closer to the y-axis. So it's going to end up being a horizontal compression. Reflection and compression. So if I get my axis out here, you're probably getting tired of hearing me say that. My untransformed function used to be at 0, 0, 1 and 1, 4 and 2, 9, 4, 5, 6, 7, 8, 9 and 3, 16 and 4, but I've lost those dots. So, here we go. This dot here is 1, 2, 3, 4, 5, 6, 7, 8, 9 squares away from the y-axis. Two things happen because of this k value. First, it gets reflected so that it's 1, 2, 3, 4, 5, 6, 7, 8, 9 squares on the left instead of the right. So I've reflected it. Now that 3 says I should get there 3 times as fast, which means it should take a third as long. A third of 9 is only 3 squares, so I'm there. This dot was reflected and then crushed. This one, reflected, would be 4 squares over. A third of 4 is 1.3. That's here. This dot was reflected. A third of 1 is a third. And this guy gets to stay right where he is. Now, I maybe have some room for more of these dots. There was one at 16 over here. So if I reflect it, it's 16 on that side, and then 16, a third of 16 is only 5.33. So I'd be at 1, 2, 3, 4, 5, and a third. This one used to be 25 squares that way, so reflect it, it's 25 squares this way. A third of 25 is 8.3. 1, 2, 3, 4, 5, 6, 7, 8.3. And I get this lovely square root function happening on this side of the axis. Now notice, negative x's are allowed in this one. and that's weird. You're not supposed to be able to take a square root of a negative, but look at what happens in this function. So you pick negative 4. It's right there. Negative 4 goes in here. Negative 4 times negative 3 is positive 12. And that I can square root. So positive 12 square root of that is somewhere between 3 and 4. So notice that my function is somewhere between 3 and 4.
You can sketch a cosine that has both an A-type transformation, which affects it this way, and a K-type transformation, which affects it this way. So first things first, the cosine pattern has to fit inside of a rectangle that is 360 degrees long. That rectangle has a midline in it. And the cosine pattern is start high, end high, trough dead center, and then zero out halfway between those, like so. More or less. So when I set my grid up, keeping in mind that this thing has to be 360 degrees long, actually moving up by 1, 2, 3, 4 on my x-axis is going to take forever. I'm never going to get the whole pattern. So I'm going to have to choose a scale, and I like to go up by 30 degrees. I think it gives you a good picture of your function. So I'm going to put in my x-axis here. That's the y-axis, actually. It'll be a long day. Goes my x-axis. That's just terrible. There we go. So this isn't 1, 2, 3. We're going up 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. And going the other way, 30, 60, negative 90, 180, negative 270. And if you've already changed the x-axis to allow this thing to fit on there, then you might as well change the y-axis to make the curve nice. So I found that if you go up by 0.5, you get a curve that's tall enough you can actually see how the thing moves around. So that would be 0.5. That makes this 1. This would be 2. Skip 1, 3. Skip 1, 4. Skip 5. And negative 1. Negative 2. 3. Negative 4. Negative 5. Okay. So once my grid is established, I would look for translations, which I don't have any, so I don't have to shift this thing around. I just need to put on this box, right, the 360 degree long rectangle. So starting from here, 360 degrees is there, and draw on the stop line. Open that straight up and down. And normally, a cosine goes up 1 and down 1 from its basic pattern, or from its midline. But this basic pattern has been modified by this A-type transformation here. So what's that going to do to my cosine pattern? Well, first, this is sort of the translated version, or transformed version. That rectangle won't be 1 up and 1 down anymore. It will be 2 up and 2 down because its height has been doubled. And this negative here is going to flip the function this way. So instead of starting high and ending high, it starts low and ends low. Peaks in the center, zeros out there. So this is the pattern I need to draw in each of these rectangles. So I'm going to draw in some scaffolding then. My peaks aren't going to land on 1 this time. They're going to land on 2. And dash a line in like that. My troughs aren't going to land on -1 anymore because of this transformation factor. They're going to land on -2. You can start to see that it's been blown up this way. And to handle this K-type here, that's just telling me I need 3 full cycles in 360 degrees, as the axes have been accelerated. So you get more function in the same amount of space. So used to be 1 full wave fit in here. Now I need to fit 3 full waves. So I'm just going to have to chop this rectangle up into 3 equally sized pieces. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Can I skip a grid line? I think I did. 360 got a bit far on me. 2. There we go. 12 squares, and I need to fit 3 full cycles in there. So if you chop 12 up into 3 equally sized parts, that's 4 squares each. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Perfect. Can keep going that way because these functions go on forever. 1, 2, 3, 4. 1, 2, 3, 4. So I have expanded the rectangle vertically because of this A-type transformation. I have adjusted the size of the rectangle horizontally because of the K-type. I just have to map this reflected cosine into each of those boxes. So pick a box. Let me pick this one. Looks like it starts low, ends low, start low, end low. Peak exactly halfway, and then you zero halfway between those. So I've got this crazy looking thing here. Something like that. So one's not enough. I have to map that pattern into every rectangle. So start low, end low, peak halfway, zero halfway. Start low, end low, peak halfway, zero out. Start low, end low, peak in the middle, zero out. Start low, end low, peak in the middle, zero out. And I've got enough dots to sketch in this curve. Etc. So the trick to a translated cosine or sine function too is think about the rectangle that the basic function would fit in, and then you're going to make it taller based on your a value, and you're going to have to fit more boxes into the normal rectangle based on this. So if this number was 6, I would have to fit 6 rectangles in this box. If this number was 12, I would have to fit 12 rectangles into this box. It's always trying to shove it into 360 degrees. So I think that's it. You just need to be able to spot whether it's been reflected like this or reflected like this. Stretch your rectangle with your scaffolding so that you know where to aim for, and draw on your dot patterns, low, low, high, etc., and off you go.
For the last example, I'm going to use base 2 exponential as my basic function. I'm going to generate the pattern there. We have typically used x values of -2 minus 1, 0, 1, 2, 3, and maybe 4. Those are your x's. 2 to the exponent negative 2 is 1 over 4. 2 to the exponent negative 1 is 1 over 2. Anything to the exponent 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4 is 16. And the function that I'm going to try and sketch for you is g of x equals negative 1/4 2 to the negative 1/3 x. Now, you notice that there's a multiplication factor out front, which is negative, and a multiplication factor inside the function, which is also negative. So I have both a and k values here. I have an a value of negative 1/4. Now that is a reflection. This is a vertical reflection. And when an a value is less than 1, it takes all of your values and drags them closer to the x-axis. So that's a compression. I have a k value of negative 1/3. And the negative means that it is a reflection, so I have a horizontal and a k value of that's less than 1 makes your x values less effective, which means you have to go further out in the x in order to get the same punch. So that takes all of your dots and blows them out, or dilates them away from the y-axis. So horizontal reflection and dilation. Or stretch, whichever word you prefer to use. So, for the last time in this video, summon the axis. Draw on my untranslated axis. And I'm going to map my basic pattern on there. Negative 2 and 1/4, negative 1 and 1/2, 0 and 1, 1 and 2, 2 and 4, 3 and 4, 5, 6, 7, 8, and 4 and 16. So we're going to do these dots one at a time. Start with this one, just because it's up and in the way. So this dot, first off, I have to reflect it in A. That would put it here. Then I have to reflect it in K, which would put it here. Then I have to make it 1/4 of what its normal height was. It used to be 8, so now it's only 2. And it needs to be blown 3 times further away from the axis than it used to be. So it is currently 3, so now it will be at 9. So, reflected vertically, reflected horizontally, made 1/4 as tall and thrice as far. Check. Now we need to do this one. This is at 2 and 4. Reflect it, 1/4 of its normal height, and thrice as far. So instead of 2, I should be at 6. Check. This one, over 1 up 2. Reflect it, 1/4 of its normal height, and 3 times as far as it used to be. This one, reflect it, half its height, or 1/4 of its height, sorry, and 1/3 as far as it used to be. This one, reflect it, reflect it. Half, a quarter of its normal height, and 3 times as far as it used to be. I keep saying half. I have halves on the brain, sorry. Do you notice I've got this feature happening here? My horizontal asymptote, which used to be on the left side above the axis, is now on the right side and below the axis because it got flipped twice. So if I sketch this in, my horizontal asymptote is over here. You get a function that looks like that. An exponential that is not only upside down, but also backwards.